In this video, we are going to learn how to prove the Euler's formula for the planar graph. It states that suppose G is a connected planar simple graph with total number of edges as a E and vertices V. Let's suppose R is defined the number of regions in a planar representation of G, then the total region is calculated as number of edges in a graph minus number of vertices in a graph plus 2. So we need to prove this statement is true for every planar connected simple graph. Connected graph means there is a path between each and every pair of vertices. Planar means there is a no intersection of the edges in a plane of the given graph. Simple graph means no multiple edges, no self loop in a graph. Now how to prove this one? So we shall prove this result by mathematical induction. So for that, first we will take the base case. Base case means we will check whether this result is true for certain graphs, like starting with the graph. Graph means it consists of non-empty vertex set and the edge set E. So let's suppose we have the graph that is written by G1 that contains only one vertex. So if we have a one vertex in a graph where V1 represents the number of vertices in G1 graph, then how many edges we can take in this case? As the graph is connected, planar as well as a simple, it means there is a no edge. Why? Because we cannot take the self loop in this case. If we take self loop in this case, then the graph is not the simple one. Thus, we can say that there is a no edge in a graph to fulfill this condition because we are considering the graph as the connected planar and the simple. So total number of edges in this case is 0. And how many regions we are getting according to this graph? That is the one entire plane. Hence the number of regions for this graph is 1. It means we have considered graph G1 that consists of one vertex. Now check whether the formula hold in this case or not. For the G1 graph, the formula is the number of regions is equal to the number of edges minus number of vertices plus 2. Number of edges in this case we have 0 minus vertices 1 plus 2. This is equal to 1. Whether the number of regions for this graph is 1? Yes. It means the formula holds in this base case. Now let's introduce a new graph with the help of G1 and name it as a G2. So how we can introduce a new graph with the help of previous one? We can add a new vertex into this graph. We need to fulfill this condition along with taking a new vertex. The condition is the graph must be planar and it is a planar. The graph must be simple and it is a simple. The graph must be connected but it is not a connected. It means we need to introduce an edge between these two vertices. Now we cannot take multiple edges and the self loop because the graph is simple. So second sub case we have taken in this case as if the number of vertices are 2, then number of edges in that graph is equal to 1 under this condition, and reason we are getting as entire plane, so that is 1. Let's check it for this case whether this formula is true or not. For G2 graph, the number of regions is equal to the number of edges in a G2 graph minus number of vertices in a G2 graph plus 2. The value of number of edges in a G2 graph is 1. Number of vertices in a G2 graph is 2 plus 2. This is further is equal to 1. Now whether the number of region is equal to 1? Yes. It means the formula holds in this base case. So this is the first step of the mathematical induction where we have considered the two sub cases of the base case with one vertex in a graph that is represented by G1. We can introduce a new graph with the help of G1 by adding a new vertex. For that we need to introduce the new edge because we need a connected graph. Now we can move towards the inductive hypothesis. That is the second step of the mathematical induction. The inductive hypothesis we are taking as, suppose we have any GK graph that is connected, planar, simple, with total number of vertices as Vk, total number of edges represented by Ek, and the total number of regions are Rk. Do not think that there are k vertices. We do know what is a gk step. Maybe there are 5 vertices, maybe there are 6 vertices. But that count is represented by vk. Whereas the number of edges in that graph is represented by ek. And the number of regions is represented by rk. And we assume that this result holds, means number of regions in GK graph is equal to the number of edges in that graph minus the number of vertices in a GK graph plus 2. Now we will go to the next step, that is the inductive step. In this case, we will introduce a new graph that is a GK plus 1 with the help of GK. So, in this case, we must show that the formula holds for GK plus 1 graph, that is obtained from GK graph with two possibilities. What are those possibilities? Suppose we have this as a GK graph. From here, we need to obtain a new graph. We have two possibilities. First possibility is we can add an edge in this graph. So if we are adding an edge, we need to make sure the graph must be connected, planar and simple. For simple, it means we cannot take the multiple edges between any two pair of distinct vertices, or we cannot take a self loop. If we are adding an edge, we need to add that edge between non-adjacent vertices. Like in this case, these two vertices are not connected directly. So we can take an edge directly from this vertex to this, or from this vertex to this. And if we are joining these two vertices, make sure the graph is planar. Graph is planar means no intersection of the edge. So we can combine these two vertices by taking an edge from the outer side. So we have added a new edge between the existing vertices and graph is connected, planar as well as simple. So we are getting a new graph that is a GK plus 1. So the first sub case we are taking in this case as adding an edge between two existing vertices. So according to this, what is the difference between the previous graph and this graph? Then number of vertices in a current graph, whether it is changed? No. Whatever the count we have in the previous case, the same count we have in new graph. Now, what about the edges? Whether the edges are changed? Yes, that is increased by 1. So, we can say that the total number of edges in a new graph is equal to the number of edges in a previous graph plus 1. Now, what is the impact on the number of regions? Number of regions in this case is increased by 1 because the outer region is divided into two parts and the rest of the regions are as it is. So we can say that number of region in a previous graph plus 1. This is the first case we need to take. What can be the second case? Now suppose if we are not adding an edge between existing two vertices, what we can do? In that case, we can add a new vertex to get a new graph. But the graph must be connected. It means this vertex must be connected with any of one of the existing vertex. So let's suppose we are connecting this vertex with this. According to this one, what we have done in the sub case 2, to obtain a new graph from the GK graph, what we have done, we have added a new vertex and connected it by an edge to an existing vertex. With this, what is the change in a graph we have? The number of vertices in a new graph, that is increased by 1. So we can have the number of vertices in a previous graph plus 1. Number of edges, that is also increased by 1. So previous edges count plus 1. Now number of regions, whether this edge and vertex divide the region into two parts? No. Whatever the count we have in the previous case, the same count we have in this case. So in this case, the number of regions are same. So under these two sub cases, we need to identify whether this result is true or not. Now in the next step, what we need to do? In both the cases, we need to check the formula. Now check the formula for the both the cases. So as per the new graph, the condition we have, number of regions in a new graph is equal to the number of edges in a new graph minus number of vertices in a new graph plus 2. Plug in the value in this case. What we have, regions are increased by 1. So we can write this is RK plus 1. Edges are number of edges in a previous case plus 1 minus vertices are as it is plus 2. Simplify this. This plus 1 and this plus 1 is get cancelled. From here we have RK is equal to number of edges in a GK graph minus number of vertices in a GK graph plus 2. Now what is the answer we are getting for the second case? For this case, plug in the values in this form. What we have, this is RK is equal to number of edges are increased by 1. So total number of edges in a previous case plus 1 minus vertices are, that is VK plus 1. Put it into the bracket form because we have the negative sign here, plus 2. This is equal to number of edges in a GK graph plus 1 minus number of vertices in a GK graph minus 1 plus 2. Minus 1 plus 1 is get cancelled. Finally, we have this form. In both the cases, we are getting a same form. Whether this form is true? Yes. How? By the inductive hypothesis. In inductive hypothesis, we have already assumed that this result holds. And here we can write This holds by hypothesis. And similarly, we can write this result holds by hypothesis. If this result holds, it means the formula for the gk plus 1 graph is also true. And finally, we can conclude Euler's formula is true for every connected planar simple graph G. So this is how we can prove that the Euler's formula is applicable for the planar connected simple graph.